Okay, hydrocarbons. Carbon and hydrogen compounds. Those are the main. Okay? You can also have oxygen, nitrogen, halogens, which are fluorine, chlorine, iodine, but mainly carbon and hydrogen. That forms the backbone. And all of these are going to be covalently bonded. So this relates back to Chapter 5 and that Lab 3 with the polarity and the molecular geometry. So this hydrocarbons totally goes back there. So you know how you had like two kinds of bonding, ionic and covalent? So ionic was Chapter 4, where opposite charges attract. And Chapter 5 was covalent bonding, where the bonds are shared electrons. Okay? So there's two kinds of sciences. What they call inorganic chemistry is the ionic stuff and metals, and organic chemistry, which is what this chapter is, which is all covalently bonded stuff. So what makes organic chemistry unique is that basically carbon bonds to other carbons. Okay, so carbon needs four bonds to fulfill its octet, which you're very familiar with. Remember this compound, CH4 was the first one. It's called methane. Had a Lewis structure of this, or in 3D it was tetrahedral, and wound up being non-polar when you took the geometry and the bond polarities into play. Another one that you did was this, which is C2H6. Remember that one? It was on the second page of that lab. That happens to be called ethane. Each carbon is also tetrahedral, and it's non-polar also. So here's a good example. Both examples show 4 bonds to carbon, and the carbon can bond to itself once you get into more than one carbon. You might also remember this one, C2H4. That's called ethene. Now you're going to begin to understand the names of these. Not quite yet. I'm still bouncing you back to old material. This was trigonal planar, and symmetry and bond polarity makes it nonpolar also. And you remember when we did that one with the models, you couldn't rotate the hydrogens, right? Because the double bond made it rigid. And that's true in real life. The single bonds rotate, and the double bonds don't rotate at all. So there's something I want you to memorize, and it's really the only thing I want you to memorize, and you're going to memorize it one way or the other because you're going to use it so much. I want you to learn to count from 1 to 10. Meth, eth, prop, but, pent, hex, hepta, oct, non, and dec. You're probably familiar with some of these anyway. You know what an octagon is, right? It's an 8-sided deal. A hexagon is a 6-sided deal. But you probably never thought of a rectangle or a square as a butagon, or a triangle as a propagon, but it would be. So some of these you know from like geometry. And then in the hydrocarbons, there's 3 main classes. Alkanes, which are all single bonded compounds. Alkenes, which are double bonded, and alkynes, triple bonded. Okay? So check this out. Methane, which you've heard a few times now, because we did it in reactions. We combusted it with oxygen. It was the first balancing reaction we did, almost. Look, meth is 1 carbon. See that? Look, meth is 1. That means 1 carbon. Ane, it's an alkane. It's all single bonded. Look at this. Ethane, 2 carbons. Eth, 2. Ane, single bonded compound. Ethene, 2 carbons. Ene, it's an alkene, double bonded. Isn't that cool? It's cool, right? Okay, so what would be ethine? Triple, right? So it's 2 carbons, triple bonded. Now, carbon gets 4 bonds, so there's only going to be an extra hydrogen on each carbon. So basically, look, you take 2 hydrogens away off of each carbon, you make a double bond. Take 2 hydrogens away, so a bond replaces 2 hydrogens. But the bottom line is this carbon always gets 4 bonds. And that is ethene, and it's, of course, formula C2H2. What geometry would it be? So this carbon has 2 satellites and no lone pairs. That makes it linear, and it would be nonpolar. So, and the system gets more complex, but This is basically chapter 12 and 13. 12 focuses mainly on only the alkanes, which we'll do first, and then it goes into the alkenes and alkynes for chapter 13. But the bottom line is this is all organic chemistry. Everything's covalently bonded and focusing mainly on carbon because carbon can bond to itself very well. Okay? And it's very stable. So any of your plastics, nylons, or nylon rope, any plastic toys, the spatulas that are plastic, or that used for cooking, all of that is based on organic chemistry. A little bit more complex chemistry called polymers. Poly just means many, so many units. Mer is unit. So that's just many of these connecting one after another. That's what plastics are. Okay, and the first one was nylon, developed in the 1920s. And DuPont made a fortune on nylon, just for women's legs. Then they realized that they can weave it, nylon, the threads, and made rope and sails and all those other nylon things that we use to pull trucks and whatever. Okay, so we got methane, ethane. You can do propane, right? Okay, yes, that's the gas in the white tank underneath the grill. Well, it'll have 3 carbons, all single bonded. Hydrogens to fill up all 4 bonds. C3H8. Now, I'm starting to get a little nutso here, okay? Because now there's lots of bonds. I'm only at 3 carbons, right? But now there's lots of hydrogens, lots of carbons. Your book likes to do what they call a condensed form. This is like the full form. And there is an online lecture for this called Organic Expressions. It's only 2 pages, and it's mostly a bunch of pictures to help you, like there'll be a block, and it'll be like the name, the formula, the full form. Then there's the condensed form, which is this. Okay, see, look. C3, C2, C3. Okay, your book uses this a lot. And then there's another form called the line or stick form. It's this. This one is sometimes the hardest for people to grasp. An end or a corner is a carbon. So think of the line as the bond between the carbons. The hydrogens are there, of course, because carbon still needs 4 bonds. They're just implied. All right? So the hydrogens here in the stick form are there. They're just implied. Okay, so all of these are propane. If I were to do ethane, now methane I can't really do, it'd just be this. Ethane is a little bit dumber too, it's like this. But ethene would be this. Okay, those are both the carbons and the 2 hydrogens are around it. So it's like the bonds, you just show the bonds between the carbons. And then ethyne would be this. But it doesn't make sense. It starts making sense with more than 3 carbons, the stick form. So what about butane? Draw butane in stick form. So look up what but means. Okay, so now you know why I want you to memorize that, because you need to know. As soon as you draw a line, it's 2, right? So 2, 3, 4. That's butane. And if I were to convert that into condensed form, okay, look, carbon. How many hydrogens? 3. Carbon. See, this carbon has 2 bonds drawn to it, right? So that means it needs 2 more, 2 more to fill the hydrogens. So CH2, same thing, CH2, and then the end is CH3. That's the condensed. And then the full would be this mess. I'm not going to do this anymore. And the shortcut to the geometries is when carbon has 4 single bonds, it's tetrahedral, like an ethane or methane. When carbon has 3 bonds, or 3 fellows around it, or a double bond, it's going to be trigonal planar. And when carbon has a triple bond, it's going to be linear. Draw octanes in stick and condensed form. See how you do. Octane. It's the stuff in your gas tank. And we reacted that with oxygen also. 2, 3, 4, 5, 6, 7, 8. CH3. CH2. 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 CH3. there's a quicker way to do that. Could be this. You'll see this in your book too. So look, all these CH2s, there's just 6 of them. Okay, so that covers all what they call the normal octanes, meaning they're straight across, they're linear. But things can branch, and that's where they get a little bit more complicated. So what if I took this octane and I put a branch on it, or 2? Now the root is still octane. Okay, so I'll just number my carbons straight across. That's called the main chain. So the longest chain, the main chain, is the longest chain. And then I have 2 branches. Those branches are 1 carbon branches, right? You don't count the carbon in the main chain. You count the carbon off the main chain. So there's just 1 carbon off the main chain. So that's a methyl. Put YL at the end. YL means a branch. And that's a methyl group. So this is a methyl group, and so is this. There's 2 of them. So first you do the positions. This is 2, 3. There's a methyl at 2, and there's a methyl at 3. Di for 2, methyl octane. That's the name of that stuff. 2, 3, dimethyl octane. You can have this. 2, 3, 4, 5, 6, 7, 8. What would that be called? 2, 2. You would say it twice, yeah. 2, 2, dimethyl octane. You can have this. 3, 4, 5, 6, 7, 8. You can have, okay, let's number just so we don't lose it. Okay, so still octane is our base. How many methyl groups are drawn? 4. There's 1 off of 3, 1 off of 4, and 2 off of 5. Okay, so you would say 3, 4, 5, 5, tetramethyl. Tetra's 4. Tetramethyl octane.
Where did the methyl come from then?
The methyl is the branch off of the main chain. It's only 1 carbon.
Okay.
So the meth from 1. And the YL means it's a branch.
You have to make sure the branches said one of them was 2 carbons and the actual 1 carbon.
Okay. Let's do octane again. 4, 5, 6, 7, 8. Okay. Yes, you could have a branch that's more than 1 carbon. Okay. What's this one? Is that a 1 or 2 carbon? 1. So that's a methyl. That's a methyl. What's that called? Ethyl. It's 2 carbons. Don't count the carbon in the main chain. So 1, 2. Same thing here. 1, 2. So both of those are ethyls. Love ethyl. Best friends with Lucy. Okay, so let's name it. First number your main chain. I'm just showing you the system. In a minute, I'm going to give you harder. Okay? Now, then you say which comes first, the methyls or the ethyls in the name. You go by alphabetical. So E is before M. So you say 4, 5, always name the positions, diethyl. Okay, positions of the ethyls, di for 2 of them, total, dash, 2, 3, dimethyl, and then the root is octane. And these are all real compounds. I'm just making them up on the board, but you can make all of these. You can find all of these in nature. Okay, name that one. I'll give you a minute. It's 8 carbons across, just so you're not counting by weirdness. Okay. When you first come to a structure, very first thing to do is find the longest chain. Okay? Now I'm getting more complex with these, so it's not necessarily going to be so easy to find the longest chain. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Okay, so there's 2 8s, right? We'll just go straight across, that's fine. The second rule is you start, so this is my main chain, right? This is what I keep in my head. Everyone looking? So straight across is my 8, it's my longest chain. Then the second rule is I start the end of my numbering. Like I could start 1 here or I could start 1 here, right? You always start number 1 where the branch is the closest, which is here. Okay, so 1 happens to go from left to right on this one. So I always number my main chain for 2 reasons. It highlights the main chain in my head, sort of like highlighting in your book. The second thing it does is shows you the positions of your branches. Okay? So first rule, longest chain is your main chain. That sets up your root name. So we have octane again. And then my branches, I have what at 2? What's the position 2? Methyl. What's a position 3? Ethyl. And what's a position 4? 1, 2, 3. Propyl. Okay. Alphabetical order. E, M, P. Oh, EMP. Electromagnetic pulse. Okay, so we got 3 ethyl, 2 methyl, 4 propyl, octane.
So you wouldn't use mono?
Huh?
You wouldn't use mono?
No, that's like 1 before X. Any questions? How are we doing? So this chapter and the next chapter doesn't have any math in it, but you have to get your brain around twisting it, twisting this stuff all around and still getting the right structure. So there's more mental manipulation instead of mathematical manipulation. Now you're going to switch gears into like conceptual manipulation, okay? So it's not necessarily easier, it's just a different kind of driving. All right, you don't have math to rely on, and you're not going to use your calculator. Now you're going to use your brains. All right, so here's one. Let's see. Longest chain's the main chain. That's the first rule. So some people would look at this and just go straight across. 1, 2, 3, 4, 5. They'd get the answer wrong. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. It's pretty long. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so the longest was this way, right? Okay, so I keep that in my head for a moment, and then I figure out where the first branch is. So let's see, 1, 2, 3, 4. 1, 2, 3. Okay, we'll start 1 over here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that makes it easier to see the branches too, right? And the positions. So, what do I have on 3? Right? 5? Right? 4? Yeah? Okay, good. So let's see, we got 4 ethyl. 3, 5 dimethyl octane. So, go ahead.
And you're putting the di to show that it's 2.
That they're 2 separate methyls.
Okay, alright.
Now, if I had the name, it's usually easier. Start with the root, octane, draw out 8. 2, 3, 4, 5, 6, 7, 8. And then on 4, 2, 3, 4, put an ethyl. And on 3, a methyl. And 5. So they're the same structure. Well, and the thing is those single bonds rotate, right? So this actually can be a real configuration. But in the book, we tend to draw it nice and neat, drawn out so it's easy to read. But in reality, it could be all twisty and gnarly and like that. So they're both the same structures. This one's drawn out to where it's more readable. This is actually more realistic. And there would be thousands of other configurations all twisting and turning around each other. Okay, pop quiz. How many hydrogens are on that carbon? Everyone agree with 3? Yeah? So to the end of that line is a carbon. That line is a bond drawn to that carbon. Carbon needs 4 bonds, so 4 minus 1 is 3 implied hydrogens. Okay? How many hydrogens on that carbon? 1. There's 3 lines drawn to that carbon, right? Because those lines are from other carbons, right? So what's drawn is 3 carbon-carbon bonds to that carbon. That leaves you with 1 implied hydrogen. Everyone follow me? How many hydrogens on this carbon? 2. Yeah, there's 2 drawn bonds from other carbons. So there's 2 hydrogens to make up the difference. So in chapter 12, you'll see at the bottom of page 381, you have 4 kinds of carbons, what they call primary, secondary, tertiary, and quaternary. And that's really based on the hydrogens that are around that carbon. So a primary carbon has 3 hydrogens around it. So look, this is a primary, this is a primary, 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 primary. See that? A primary carbon has 3 hydrogens. The R is anything else. It could be another carbon, it could be an oxygen, it could be a fluorine. So this number of hydrogens around the carbon directly relate to this primary, secondary, tertiary thing. All right, look, this is a secondary carbon, right? Has 2 hydrogens. So that's a secondary. That little degree means airy. Primary, secondary. Okay, look, this is a secondary, secondary, secondary. Tertiary, look, has 1 hydrogen, right? The rest are other carbons or other stuff. So look, tertiary, tertiary, tertiary. And then also on that page, you see in the table 12.4, you see the methyl group is a CH3, right? The ethyl. See the red line there? That means it's bonded to another carbon on the main chain. So look, ethyl. Here's that red line. Okay? Here's the CH2. Here's the CH3. What I'm doing is I'm helping you translate between the stick and the condensed form. Those.
That has a red line and attaches to the main chain.
Yeah, the red line means it's attaching to the main chain. Okay? Propyl. Look, here's your red line. CH2. Okay, look in the table under N-propyl. N means normal, means straight across. CH, red line, CH2, CH2, CH3. See how that's bonded? Okay, but then there's another kind of propyl, right? What's it called? Isopropyl. You ever hear of isopropyl alcohol? Okay, that's rubbing alcohol, right? It looks something like this. Okay, so look. Here's the red line, right? Connecting to the main chain. CH, right? There's only 1 hydrogen on that carbon, right? Mm-hmm. See that? And then there's 2 CH3s connected to that CH. Okay? It's important for you to translate between these different forms. If you've got that translation down, you got 12, most of chapter 12 pretty much nailed. Okay, Okay, then it's a matter of naming. Okay, let's name this one for fun. 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's octane still. 1, 2, 3, 4. 1, 2, 3, 4. So it doesn't matter which end we go to. Actually, you go to the more you start. So the branches are the same length, same distance, right? They're both 4 from the end, whether I start from the left or the right. This one's more complex. This ISO one. So we'll go with that. 1, 2, 3, 4, 5, 6, 7, 8. So you've got isopropyl, 4 isopropyl, 5 propyl, octane. Throw that one out. It's a gnarly mess. Okay, here we go. I don't want you to do this one. I want to walk you through it. Okay, first rule, longest chain is the main chain. So find the longest chain. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, either of those will be the same, right? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. What did I get to? Thanks. It was this way.
Yeah.
All right. 1, 2. So let's do that. So this way. Okay, 10. And find the first branch. 1, 2, 3. 1, 2, 3, 4. So start from this end. That's the second rule. Start your numbering of the main chain where the closest branch is. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now that makes it a whole lot easier. It brings a lot of order to chaos, right? Because now we know quite a bit. We know the main chain. We know where the first branch is. We know what the branches are. Okay? All right. So let's identify our branches. Okay, look closely now at 381. Now some of them are easy, right? What is this? Huh? Right, methyl. So that's a 1 carbon. Same thing here on 7, right? What's this on 3? Ethyl. Yes, 2 carbons. Now, I made these 2 funky for a good reason, because look at that table on there. Look, there are 4 carbons. That's the first thing to see. Look, here's the main chain carbon, right? So 1, 2, 3, 4. Also here, look, main chain. 1, 2, 3, 4. They're both butyls. Okay, look at the bottom there of page of 12.4 table. N-butyl is 4 carbons straight across, right? Okay, that's what N means. It just means normal or straight across. Look at sec-butyl. Okay? Are either of these sec-butyl? Look carefully. The one on 6s. Yes, look. Here's the main chain, red line. Going to a CH. Look at sec. Goes to a CH. On one side of the CH is a CH3. See that? On the other side of the CH is a CH2, CH3. So this is sec-butyl. Which butyl is that on 5? No, it's tert. Yeah, look. Here's the red line off the main chain. Goes to a C. Look, see this carbon? Does this carbon have any hydrogens? Look at it on the board. There's 4 lines drawn to it, right? So that means there's 0 hydrogens. And 0 hydrogens makes it a tertiary or a quaternary carbon. Go back to, look at the bottom of the page. See, there's 4 R groups there, quaternary. See that? There's no hydrogens. That's a quaternary carbon. Everyone follow me? So now look back at tert-butyl. So you have the red line going to just the carbon, and then there's 3 CH3s around it. That's tert-butyl. Okay, so let's name this thing. Okay, so what's the root name first? Decane. 10 is dec. All single bonded dec. Okay, let's alphabetize them. E, M, B. Okay, butyls are first because they're B. Sec before T. So 6 sec-butyl. 5 tert-butyl. 3 ethyl. 4, 7 dimethyl decene. I'm giving you like really complex because I'm pulling out a lot of points, okay? I don't think you'll see them this complex, but I want you to get your eye used to translating. Now there's only one other kind of alkane in chapter 12, which is when they close in on themselves, become circles. They're cyclic. This is called a cyclo. How many carbons are drawn? 3. So that's a cyclopropane. So when you see it closing in on itself, it's a cyclo. Now that doesn't actually exist because it's too much strain to make a triangle with 3 carbons. The bonds can't handle it. But you can, in rare circumstances, do a cyclobutane. Now you lose 2 hydrogens when you close it in on itself. So for instance, on the decane, on propane, it's CH3, CH2, CH3, right? You take a hydrogen off of each end, and now it closes in. See, this is a CH2, right? This is a CH2, right? They're all CH2s. So that's what you did, is you took hydrogen off of each end and it closes in on itself. Okay, when they're cyclo, those are automatically the main chain. So you can have branching off of cyclo also. That's my little TV. Remember the old TVs with the antenna? Okay, so the main chain, when it's cyclo, the main chain is already the cyclo part. So what is that? A cyclo what? Pentane, right? Because there's 5 carbons in the main chain. You start your numbering again where the branching is the most intense. So that'd be here 1. So that's a 1, 1, dimethyl, cyclo, pentane. Okay, what's the main chain? What's the name? Hexane. Yep, cyclohexane. Now, the numbering 1 would be where the most complex branch is, which is obviously this Jesus on the hill kind of thing. Okay? Now, some people might do this to number their main chain. But you always want it, and the reason for starting your number on this where the branch is the closest is because you want to reduce your numbering. So does that reduce your numbering? No. So you would circle the other way. You'd go number 2 so that your second branch is minimized. So instead of it being 6, it should be 2. So you would cycle you would go counterclockwise as opposed to clockwise. Okay, so that would be, so what branch is that, the cross? What kind of, how many carbons on it, first of all? Right, 4 carbons. Look on your table there and figure out which kind of butyl that is. What kind of butyl is that? Tert, very good. Okay, so we've got 1 tert-butyl, 2 methyl cyclohexane.
So if that little branch up top were down there on the bottom, you would go the other direction.
Right. Right. This would be equal. Actually, let's say it was like this. That's the same exact thing because it's the 1, 2.
Okay.
And in fact, in reality, this thing's rotating in 3 dimensions in solution anyway. It's rotating all over the place. Okay? That's chapter 12. They get a little bit into reactions, but it's not that rough. It's mostly this naming and what's the possibilities. So look at organic expressions, okay? It'll help your eye with converting between condensed, full, stick, all of that. Okay? Practice problems, right? Let's do chapter 13. Chapter 13 is just an extension of 12, where they add in double and triple bonds. The foundation is all there now, though. What's the name of that? Hex? Ane. Yes. Okay? Now we have double bond in there. It would look like this. That could be there. So in the stick form, it's just like that. That's a double bond. You can also have double bond here. You can have double bond here. You can have double bond there. So see how the double bonds are in stick form? Okay, now when you have double bonds or triple bonds, those take precedent over the branching when it comes to the end of the numbering. Okay, so let's just say we had a branch here on that one, okay, methyl. So before I said you start your numbering where the first branch is, right? Which would be on this side, on the right side. But when you have a double or triple bond, that takes precedence over branching. So now the end would be here. So this would be 1, 2, 3, 4, 5, 6. So this would be 5-methyl, 1-hexene. So the 1 is for the double bond, ene is for double bond. Okay? And, okay, look, second one. I start my numbering where the double bond is closest. Okay? Number my main chain again, hexene. Now it's 2-hexene. There's no branches on this one. 2-hexene. What's this one called? 1, 2, 3, 4, 5, 3 hexene. What about this one? What's this one called? Ah, she didn't get tricked. Right. Start on the other end, right. 1, 2, 3, 4, 5, 6. 2-hexene. Yep, 1.
And the hexene is because a double bond.
Yes.
Right.
Ene is alkene. Alkenes have double bonds. And you can have more than one double bond in the same molecule. Let's say here and here.
What do you do? 2-hexene?
It'd be, and in this case, it doesn't matter which end you start 1 from, right? Because here is 1, 2, and from this end it's 1, 2. So it's both in the second position. So let's just go left to right. So we'll have 2, 4 dihexene. Or the other way is hex 2, 4 diene. They just squeeze it in any way they want. I I think there's a rule which way you do it for, but I forget. I'm not an organic chemist. I only do it for fun.
Noted.
And triple bond would be the same thing, except instead of ene, you'd be "ine" with a Y-N-E. That's the only difference. Now you have to be careful because you lose, when you make a double bond, you lose 2 hydrogens, right? Around those carbons. So if I were to convert this into condensed form, let's do that. This carbon, right, has 2 bonds drawn to it, so there's only 2 hydrogens, right? So it'll be CH2, and then in the condensed form, you draw the double bonds, and then this is CH. See, there's only 1 hydrogen on that carbon, right? And then CH2, CH2, that's CH, right? So this is carbon 3, 4, CH is carbon 5, and then off of that CH is a CH3, and then CH3 on the end. So this is carbon 1, 2, 3, 4, 5, 6. Now sometimes you'll see branches in parentheses in the condensed form. That would look like this. So sometimes they see how you have to concentrate and see this CH. You know that there's 3 other carbons to this CH. So that would be this carbon before it, this carbon after it as a branch, and this carbon after it as the end of the chain. Okay? So when you see condensed, you have to look at your hydrogens too to see what all the carbons are also other bonded to. So condensed I always consider a little bit, it's a little bit confusing because you got to figure out what the hell is. Whereas stick is almost much more straightforward. You just know that the hydrogens are implied. And then here's even another way they would do it. So this 5-methyl-1-hexene could be drawn quite a few different ways in condensed form. So see this CH2 came from here 2 times, and then this CH3 3 times. So one of those is the main chain and one is considered a branch, those CH3s. Just making you aware. And then let's say we were going to do this one. It'd be CH3, CH, right? Double bond, CH, CH2, times 2, CH3.
I like the stick figure better.
Oh, I do too. Organic chemists use the stick. Here's a nice little exercise. If you ever go to the doctor and you get a sample of a prescription, right? And they'll give it to you in a little box, okay? And it'll be like 1 pill in there. Whoop-de-doo, okay? So you take the pill, but in there's this little pamphlet like this big, okay? Unfold it. It unfolds and it'll be a sheet this big. It's weird, okay? On there is the chemical formula for the drug. And it'll have the stick formula and the name. And the name will be, you won't understand all of it because some of it gets really funky, like real funky. But you'll notice there'll be some hexenes or octane or whatever in there. You'll recognize some of the name. But you'll see it's always in stick form. And they might give the formula too, like the C8H20 whatever. And from that, you can calculate the molar mass, right? Now you know the molar mass. Now you can go to grams to moles and moles to grams. Man, you're on your way. But they do that. That's real chemistry there. So you could take the sample of the drug, and you could do that with any drug. Look it up in whatever book, or even put the name. Actually, you put the name in Google, whatever drug you're taking. You go to Wikipedia. It'll show you the structure. Probably calculate the formula away for you. You're golden. You could do all the chemistry you want on the damn thing. You can figure out how many molecules are in that pill because you're taking what? 500 milligrams? Convert that into grams, convert that into moles, convert that moles into Avogadro's number of molecules. Now you know how many molecules are floating in your body when you take that one pill. And you're going to know how many receptors are going to accept that pill. So now you know how many cells are involved with taking that one pill. So this is all of everything right there. Okay, and if we were to do triple bonded one, would look like that. So that'd be 2 hex-ine. And its condensed form would look CH3. Yeah, just C, triple bonded to C. So those are both quaternary carbons, right? Because there's no hydrogens on them. CH2, twice, CH3. And just to wrap up chapter 12, well, there's 2 more subjects I need to do, is reactions. Double and triple bonds are very susceptible to reactions. Basically, a single bond, it doesn't react very much. You really have to push it. You really have to push it for a single bond to react. And that's what chapter 12 has, a couple of those reactions, but they're not real complex, and there's not a lot of them because you have to really push it. But double bonds and triple bonds, the bond is sort of out there in the open, and it's vulnerable to attack. And they go through all those in section 6, and they're pretty involved, but they come down to, summarize it, on page 429. So I want you to read section 7, of course, but they come down to page 429. But the book just shows it with 2 carbons, and that is a little bit confusing. So look, let's do it where there's less symmetry so you can follow what's going on. Okay, we'll do it with 1 butene. And we can do the condensed form of that. Okay, the first reaction is you react it with hydrogen gas and some catalyst. Catalyst is just something that helps it go. Okay, that's just a fancy word. It's another compound, another chemical that pushes the reaction. But the catalyst itself is not changed. So let's say the catalyst is some metal like platinum. It's going to stay platinum. Okay? It actually gets involved. It helps facilitate. It's sort of like a psychologist helps the marriage stay together. But they're not involved in the marriage directly. So the psychologist is still the psychologist, but hopefully the people come out with a better marriage. That's what the catalyst is. Isn't that an analogy? I'm such a dork. Okay. So what is that going to do? Okay, if you look on that 429, it's going to add the 2 hydrogens across the double bond. Okay? So all of these reactions are going to be about the double bond. Okay? And the rest of it is just going to be ignored. So think of the double bond as the vulnerable part. It's the stomach. You want to punch them in the stomach, right? So that's where you get them, in the stomach. So all you're going to get out is butane. So you add those hydrogens across the double bond, you get rid of the double bond, and now it's butane. So you wind up with CH3, CH2, CH2, CH3. That's one reaction, real simple, right? Get a little bit more complex. Now let's, instead of hydrogen, let's add a halogen. Now that could be chlorine, Cl2, it could be iodine, I2, bromine, Br2, or fluorine, F2. Okay, what's going to happen there? Okay, it's going to happen around the double bond. So basically what's going to happen is the double bond sort of splits in half, opens up around both carbons. You're going to end up with this. So let's number these carbons here. So there's our butane again. But now you're going to have a chlorine on position 2 and another chlorine on position 1. So this is still the stick form, but when a bond goes to something other than carbon, you say what you put that symbol for that element So in this case, it's chlorine. So this second carbon is bonded to chlorine now. Okay, there isn't a secret carbon between the carbon and the chlorine. It's bonded directly to chlorine, okay? All right? So this happens, this stuff would be called 1,2-dichlorobutane. But the main thing I want you to see is that chlorine, the two chlorines, went to the carbons involved in the double bond. The rest of it was completely ignored. Okay? They sort of skip over that important part, but they'll test you on it in the book.
Go figure.
Yeah. Okay, that's why I'm pointing that out. So, because I wanted to show you with a more complex molecule, to show you that the alkane part, the single bonded part of the molecule, is ignored. Okay, the next one, what they call C there, HCl. Okay, same stuff. What's going to happen? Now you have an H and a Cl. So that bond between H and Cl is going to weaken. Now there's a rule, and you'll read it in that section 7, called Markovnikov's rule. This is a Russian dude. He figured this out. And it's pretty easy. When you have an asymmetric molecule that's attacking, asymmetric meaning a hydrogen and chlorine in this case, they're not the same, it's not like two hydrogens and two chlorines like before. Now you have two different, okay? In this case, the hydrogen is going to go to the carbon that already has the most hydrogens. So that means the hydrogen is going to go to the carbon that already has the most hydrogens. So this carbon had two hydrogens, right? And this carbon only had one. This carbon, wait a minute. This carbon has two hydrogens, and this carbon has one hydrogen. So when the hydrogen is added from the HCl, it's going to go to the carbon that has the most, which is the 2. So it's going to end up on position 1. So then what you'll wind up with is simply that. And the other hydrogen was added to there. So now that's CH3, right? So this is 2-chlorobutane. And for D, yeah, it's almost the same exact thing. Markovnikov's rule. Now instead of HCl, we're doing water. Our catalyst is an acid. So water is really like this, right? It's a hoe. Okay, that hydrogen is going to end up on that first carbon again with an OH there, just like chlorine. So hydrogen goes on the carbon with the most hydrogens. And that would be 2. Okay, we like to call this hydroxide, right? But that's more for ionic bonded stuff. In organic chemistry, this is called an alcohol group. And the functional groups I have as a table under resources in Blackboard, but it's also at the beginning, it's just a copy of the beginning of chapter 12, page 365. You'll see an alcohol group there is an OH group. Page 365. And you can print out that it's the same thing under resources. Okay, I think I call it functional groups or something. But look under alcohol, you'll see it's an OH. Okay, so this is 2-butanol. The OL means alcohol group. Isopropyl alcohol. Rubbing alcohol. Iso, see how it's like a Y? Isopropyl alcohol. Oh, one thing about this, see how I drew this? Remember I told you if it's triple bonded carbon, it's linear? Mm-hmm. That's not quite right, because I drew that sort of like it's tetrahedral, didn't I? Even in stick form. So that would be better drawn like this. Yeah, so if I were to number this, like this, be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is a more accurate representation of the stick form because triple bonds are linear. And back to configuration for the double bonded. Remember the one that was like this? Remember that one? Was C2H2Cl2? And I said there were 3 possibilities. Well, I see here how the chlorines are on the same side. This double bond doesn't twist, right? So there's no way for this chlorine to rotate down to this position, right? So these chlorines are stuck being on the same side of the double bond, right? See, if I draw lines for the double bond, those chlorines are on the same side, right? That's called cis. Cis means same side in German, I think. The other possibility was this. Now they're on opposite sides, right, of the double bond. That's trans. Now the third possibility in that lab was this. That's neither cis or trans. The chlorines are in the same carbon. Okay, so that doesn't matter. So you have to have 2 groups, non-hydrogen, on 2 carbons opposite each other on the double bond to be either cis or trans. If they're on the same carbon, it doesn't matter. It doesn't make sense. Because look, this could rotate. This whole molecule could rotate. It's the same as this, right? This whole molecule can rotate, and then it's opposite, right? This chlorine would be down here, but this chlorine's up here. But they're still opposite sides of the double bond, right, for trans. And for cis, you can rotate this 180 down, and still the chlorines are on the same side of the double bond. See the difference? So that's why cis and trans, when you rotate the whole molecule, those groups are still either on the same side for cis or on the opposite side for trans. But this one is neither cis or trans because you can rotate it 180 degrees. It's still the same molecule. You didn't do anything. Now, you've heard of KFC having no trans fat, right? Anyway, you know KFC. They took out the fried. Used to be Kentucky Fried Chicken. Now it's KFC because they don't want to have fried in their name. Anyway, this cis and trans stuff is going to become more big in the lipids chapter, which is 24. But what happens is, if you have your R groups now, and those are long carbon-carbon chains, right? If they're cis, okay, so these are carbon, 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 carbon. I'm just making squiggles, but this could be like 18 carbons. This could be 12 carbons, okay? And then if you have trans, which looks like this, see, that double bond makes that part of the molecule rigid, right? Because it's not going to rotate. Well, if you have this double bond in trans, these long carbons can stack on top of each other like logs on the trucks. See how it's sort of just straight? Okay? Whereas cis, see how it's now kinked? They can't stack on top of each other because they're kinked. Whereas the trans, they could stack just like logs. So this makes the old style lard, the real heavy, white, that you're, Crisco's kind of in between. They're trying, Crisco used to be lard. They fixed it. Now it's vegetable shortening. And it's lighter. It's heavy, but it's lighter than lard. If you ever try and pick up lard that's big, it's like heavy metal food. Okay? And it feels like that, but there is nothing better than chicken made in lard, okay? Anyway, what's happening there is it's very dense because those can pack very tight like the logs on a truck. Okay? That's what trans is. And this is what all the oils and fats that you fry in are the trans kind of fat. The cis kind of fat is kinked, so they're not packed so tight. There's a lot of space in between them. They're not so dense. Does this make sense to everyone?
Yes. So is this healthier for you? Because you can break it
Yes.
down faster?
So all of the peanut oil and all of the olive oil have many kinks in the long chains because they're all cis-based. And that's good oil. So when KFC is saying no trans fat, they're actually saying two things. One is bad and one is not good. But the good side of no trans is cis, which is the kinked fat. So it's okay to have fat. You need fat to build cells because your cells are made out of phospholipid bilayers. Lipid is that fat.
Cooking their chicken in peanut oil as opposed to lard.
Yeah. Well, we're much healthier these days. You can't really find lard unless you make it yourself. I don't think you can buy lard anymore. The heaviest oil you can buy is Crisco and corn. But as long as it's in liquid form at room temperature, you're doing pretty good because it's going to be liquid in your body. Because room temperature is like 22 degrees Celsius. Our body is 37. So it's going to be a little bit less dense at the higher body temperature. So if you're cooking in liquid anything, you're pretty much not bad. But the best ones are the olives, the peanuts, and the canola. Canola tastes like crap, though. Okay, so I always do peanut. Huh? Some people can't do peanut because they're like allergic to peanut oil, right? Mm-hmm. But that's what they mean. See, this is trans fats, bad stuff. And the cis, when they say no trans fat, one of the implications is the cis. And that's perfectly fine. It's actually better. It actually can reverse some of the buildup in your arteries. Is the good oils.